Welcome to the lecture on Engineering Statistics and Linear Algebra. In my previous module, I discussed about the single random variables and few distributions related to the single random variables. So in this module, I'm going to concentrate on multiple random variables. So multiple random variable in the sense, if we are dealing with two or more random variables for the same sample space, we can call it as a multiple random variables. So we'll see one by one. The first one is, we'll see what is meant by multiple random variables. So in many applications, it is important to study two or more random variables. So defined on the same sample space. So as I told that, so I'm going to define the two or more random variables in a single sample space. And in this module, we first consider the case of two random variables and their associated distribution and also few properties related to the two random variables. So the first concept is in the multiple random variable is bivariate random variable. So bivariate random variable in the sense, so in this concept, I'm dealing with two random variables. So we can call those type of random variables or called as bivariate random variables. So let S be the sample space of random experiment. So I'm taking a sample space from the random experiment. So let me choose two random variables here, that is capital X and capital Y. So let X and Y be two random variables. Then the pair XY is called bivariate random variable or two-dimensional random vector. So we can call the bivariate random variables is also called as an two-dimensional random vector. So here I'm going to deal the two random variables in the same sample space at the same time. So we can call those type of random variables are called as an bivariate random variables. So in this module, we focus on joint characterization of two random variables here. That is, if two random variables are discrete, I am going to use joint PMF. So PMF in the sense probability mass function, and also I am going to use joint c.d.f. So joint cumulative distribution function. So for the discrete random variables, we supposed to use only joint PMF as well as joint c.d.f. And in the case of continuous random variable, we must use only joint PDF. So joint PDF in the sense joint probability density function and joint CDF. So joint CDF in the sense joint cumulative distribution function. So actually in this model, I'm going to focus only on the continuous random variables. So joint distribution function. The joint cumulative distribution function, or we can call it as joint CDF also, of two random variables capital X and capital Y is defined as the probability that the random variable capital X is less than or equal to a specified value of the real number small x. And also that the random variable of capital Y will be less than or equal to the specified value of the real number small y. So it is denoted by capital F of small x comma y. I mean these were real numbers with respect to the random variables capital X and capital Y. It is given by the probability that the random variable capital X is less than or equal to the real number small x, comma the random variable capital Y is less than or equal to the small y. So this is a formula for the cumulative distribution function in case of the joint distribution function for the continuous random variable. So now the properties of joint CDF or joint cumulative distribution function. The first property is the range of the cumulative distribution function of the joint distribution is varies between 0 and 1. That is 0 less than or equal to f of x comma y will be less than or equal to 1. The condition number 2, p of xy of minus infinity comma minus infinity will be equal to 0. So the range of the random variables capital X and capital Y will be same here. So it will be equal to 0 always. Next is the capital F of minus infinity comma y will be equal to p of x is less than or equal to minus infinity, y is less than or equal to the real number y. It will be given by 0. And similar next condition, capital F of x comma minus infinity. I mean the real number with the range of minus infinity. That is p of the random variable capital X is less than or equal to small x and capital Y is less than or equal to minus infinity. The value will be equal to 0. So this can be useful while solving the problems. Next property is p of x comma y, that is p of minus plus infinity to plus infinity, so will be equal to 1 always. So the positive limit, so if I'm taking all the random variables, all the real numbers as a positive limit like infinity to infinity, it will be equal to 1 always. So next is the f of the real number small xy is monotonically non-decreasing function of both small x and small y here. The property number 7, the capital F of x2 comma y2 plus capital F of x1 comma y1 minus capital F of x1 comma y2 minus capital F of x2 comma y1 will be equal to p of x1 less than x less than or equal to x2, y1 less than y less than or equal to y2. So this value will be always greater than or equal to 0. So this value will be always positive, not negative. Next is p of x comma infinity, sorry, f of x comma infinity will be equal to f of small x, and f of infinity comma y will be equal to f of y. So this is a formula for to obtain the marginal distributions of x and y. So from the cumulative distribution function, we can estimate the value of the marginal distribution, that is marginal cumulative distribution function, by using these formulas. So next is independent random variable. So in case of joint distribution, so I'm going to deal with here independent random variable. So if two random variables capital X and capital Y will be called as an independent, when means if capital F of x comma y will be equal to capital F of x into capital F of y. So if this condition is satisfied, we can call the random variables x and y are independent for all the real number values small x and small y. So we can call the two random variables x and y are independent if this condition is satisfied. That is capital F of x comma y will be equal to capital F of x into capital F of y. So this will be called as an independent random variables. So next is joint probability density function for continuous random variable. So I'm going to discuss here joint PDF for the continuous random variable. The joint PDF of the continuous random variable is given by, so let x comma y, I'm taking two random variables again here, capital X and capital Y, be a continuous bivariate random variables. So with c.d.f, a capital F of x comma y, and let small f of x comma y will be equal to dou square of capital F of x comma y divided by dou x into dou y. So if I differentiate the cumulative distribution function for two times, with respect to x one time, with respect to y one time, I can easily estimate the value of the probability density function, that is small f, in case of the continuous random variable. So the function small f of x comma y is called the joint probability density function of the random variables capital X and capital Y. So now the joint c.d.f can be expressed in terms of joint PDF. So now I want to find the value of joint c.d.f from the joint PDF. So from this equation I want to find the value of joint PDF. So for joint c.d.f. So for that we have to integrate this equation twice to get the value of joint c.d.f like this. So the joint c.d.f can be expressed in terms of joint c.d.f PDF as capital F of x comma y will be equal to integration minus infinity to y, integration minus infinity to x into the joint PDF function, that is small f of u comma v into du dv. So this formula we can utilize to obtain the joint c.d.f from joint PDF. So next is properties of joint probability density function. So the first condition is the small f of x comma y should be always greater than or equal to 0. So this condition must be positive always to satisfy the joint density function. Next is the integration minus infinity to plus infinity, integration minus infinity to plus infinity, the joint PDF function f of x comma y dx dy should be equal to 1. So after integrating this function with respect to x and y between the limits minus to plus infinity, the value must be equal to 1. So these two are the main properties to satisfy the function is a joint probability density function in case of continuous random variable. So any non-negative function of x comma y with a volume of 1 is valid for joint PDF also. The next condition is the probability of x1 less than x less than or equal to x2, y1 less than y less than or equal to y2 will be equal to integration of y1 to y2, x1 to x2 with the joint PDF function f of x comma y dx dy. So to represent the formula for this function, we can use the integral like this for the given limit of the random variable capital X and capital Y. So now that is the probability of an event is the volume of the joint PDF over that particular event. We can take it. So next is to estimate the marginal PDF of the joint PDF. So we can use this formula. So the small f of x will be equal to integrating f of x comma y with respect to dy. We have to do it. So we can able to estimate the value of the joint PDF of f of x. So similarly, to obtain joint PDF of f of y, we have to integrate the joint PDF function with respect to the dx to get the marginal PDF with respect to y. So next is independent random variables with respect to the joint density function. So that is two random variables x and y will be called as an independent random variables in case of joint PDF. So like how means that capital f of x comma y must be equal to capital F of x into capital F of y, and also for the now in case of joint probability density function, we have to differentiate the equation both sides. So I'm going to differentiate this equation twice with respect to x and y, and here differentiating this f of x function with respect to x and differentiating this f of y with respect to y. So I will be having the joint probability density function like this, that is small f of xy will be equal to f of x into f of y. So this is the for this with this condition we can say that the random variable, two random variables x and y are independent in case of joint probability density function. So this is for joint probability density function, and this is for joint cumulative distribution function. Okay, so in the next lecture I'm going to discuss about few more examples related to the joint c.d.f and joint PDF. Thank you.